Hello everyone and welcome to a new episode of Golang Cafe, and today we are going to talk about unit testing in Go. Today is going to be a very simple example. We're going to go through a self-contained function and how you can unit test a very simple and small function. In some of the new episodes we are going to go through some more complex scenarios on how you can use unit testing and how you can test functions that deal with external dependencies such as databases or APIs or external systems. But today we're going to just go through a very simple use case just to introduce you to the way of testing in Go. One of the first things you have to know about the Go testing is that there is a lot of tools already in the Go standard library and in the Go tooling that allow you to test in Go, so you don't have to install any dependencies, you don't have to get any dependencies or get any other external libraries to do testing in Go. So it's something you already have in the standard library. And one of the first things that you have in the standard library you have to check is the testing package. So if you just go into your command line and you type go doc testing, you will see that you have a very extensive documentation, and you will see from the start that you have a few conventions around how you write test in Go and how you run test in Go. The package testing provides already a lot of tools and all the tools you need really for writing and running unit testing in Go, and it is well integrated within the go test command, which is what we are going to use to run the test itself. And the definition of tests are going to be done by using the prefix test and then the function name or the test case name that you want to run, and you're going to have to pass the testing.T pointer to your testing function. So this is the convention that you have to use, and this is one of the examples that the package that the documentation gives you, which you have like the absolute value function, so it's testing.T test. As you can see, it starts with test, and then it has the function name or the test case name, and then you have the testing.T, which is the testing package, which allows you to drive the test to failure or to success. So this is the basics you have to know. You have to know that you have the go test command that allows you to run tests. You know that for each test case you have to define a test function that will be run, and that's pretty much it. And the files and where you store the test, you have to store the test into files that end with ._test.go, which is the convention in Go. So today we have the first thing we're going to go through is see our test case, our function, and then we are going to attempt to write a test for it and go through some of the examples and some of the gotchas around unit testing. The function for today is going to be a Fibonacci function. So the Fibonacci function is just now returning a fixed value, random value. But the Fibonacci function is basically a function that returns a number according to the Fibonacci sequence. If you haven't heard of that, the Fibonacci sequence defines two starting values for it. So obviously you start from 0, and then you have two initial values. You have 0 and 1, and you have by definition that the Fibonacci item at sequence 0 is going to be equal to 0, and the Fibonacci item at position 1 is going to be equal to 1. And then all the other Fibonacci numbers are defined as follows. So Fibonacci at position n is going to be equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. And as you know, since we have already a couple of starting points, we can then walk back and calculate any other value for the Fibonacci function. So just to go through and to let you make sure that you got what we're trying to do is just trying to calculate the value of 2, which is 2 minus 1 based on the formulas plus Fibonacci of 2 minus 2. We know that 2 minus 1 is 1, and Fibonacci of 1, this is going to be Fibonacci of 1. 2 minus 2 is 0, so this is going to be Fibonacci of 0. And so this is going to be equal to 1 because Fibonacci of 1 is what we already know here, and Fibonacci of 0 is going to be equal to 0. So ultimately Fibonacci of 2 is going to be equal to 1. because it's 1 plus 0. And you got the gist basically. So effectively now what we can do, we can define Fibonacci of any number, because we know that the Fibonacci number at certain position is equal to the sum of the previous two numbers. And here you have 0, 1, then 1, then 2, 2 plus 1 is equal to 3, 2, 3 plus 2, 5, 8, 13, and so on and so forth. This is the Fibonacci sequence. So you can write test either before or after, is up to you. Now we're just gonna go through running the test before, just because we want to see the test failing, and then as long as we change the function, we see that our tests start to pass magically. The first thing that we know that is to run tests, we just need to run the go test package. The go test command line tool command. Now you can see that you don't have any test file in our directory, and go test, what it does, it just goes into the directory and searches for file that ends for _test.go, and it attempts to run the test that are inside those files. So we have the Fibonacci.go function, and we're trying to write a test for it. So the first thing we're going to do now is create Fibonacci _test.go, which is the convention in Go to write testing files for our Go files and our package. The package is the same in our case. You can also define the package as being Fibonacci _test, but in this case bear in mind that any unexported function, any unexported type is not going to be visible inside the test. This is called black box testing. So we're just going to do white box testing. We're just going to be using the same package, so we can access unexported functions and types, just for brevity. As we see in the documentation, all tests start with the test prefix and then the name of your test case or function. So for now, we're just going to say I want to test Fibonacci 1, and then you pass the testing.T. This is also a convention, so it's going to be the same for any type of test you write. We just make sure that we import the testing package. And then we have our output value for the Fibonacci sequence that we call the Fibonacci function, and we say Fibonacci 1 is equal to, we return it to out. So now how do we check the value? How do we make the test pass or fail? So you know that in unit testing you need to make the test either to pass or to fail. Or you can skip the test if you want to, but it's not something we're going to go through today. We're just going to make sure that the test either pass or fails. And we do that by just checking testing.T. So we know that we're using the testing.T package, and we have a bunch of functions that we can use. So the testing.T is passed to every testing function, and you can call some of those functions to make the test fail. For example, by calling fail now, or by calling fatal f. Now we're going to call error or error f. And so we can then pass also a message, and we can say why the test has failed. So we just go through fib test. And when does the test fail? Well, the test fails when the output is not what we expect, but what is the value that we expect in this case? So the expected value for 1 is a 0, if you remember, because the first is 1, if you remember, sorry, because if we start with a 0 index, you will see that this is our Fibonacci sequence, 0, 1, 1, 2, 2, 3, 5, and so on. So this is the position 3, 4, and 5. So these ones here are the positions, and these one are the values of the Fibonacci. So we know that the Fibonacci 1 is going to be equal to 1, Fibonacci 0 is going to be equal to 0, Fibonacci 2 is going to be equal to 1, 3 to 2, and so forth, and so on and so forth. We can also define sequence number. We say that we're testing in 1 now, so here we just can pass sequence number. So as we said, we want to make the test to fail when the expected value is not what we are, when the output value is not what we expect. And we can call the error f function that we have seen before, and we can pass a message and say why the test has failed. has failed. So what I usually do, you can write any type of message, but it's good to it's good to set and to write down what's the expected behavior and what instead is the output that you got. So the expected behavior is that for this sequence number we expected this value, but we got this other value. So in this case, if there is any errors, we're gonna know that we have the expectation for this input value and we output value expected, but we got another value here in the output. So that's what we're gonna be able to do. Now we just go run test again, and you can see that you have a failure here. Test Fibonacci 1. Line 12, it says Fibonacci 1 was expecting 1 as an output, but got 1, 2, 3. So now we're gonna go through here. We're gonna say, okay, if we know that 0 and 1 is the first two values are fixed value by definition in the Fibonacci sequence. So if n is less than 2, then we are just going to return n itself, because obviously 0 is the same value as 0, 1 is the same value as 1, so this works. It doesn't work for the other cases, which we're gonna see in a moment, but we see that the test now passed successfully. So now we have tested the Fibonacci 1, we haven't tested Fibonacci 0. We could do that, but we want to test the Fibonacci 2 as well, so let's test Fibonacci 0 as well. How do we do that? Well, now we have this and we can just change the value here. The sequence is 0 and the expected output is 0, as we said. Go test. Let's see if it works. Okay, it works. You could also have the -v and it says the various test cases. So Fibonacci test. So now let's try with the Fibonacci 2. Let's see how it unfolds. And we can see that now we have the Fibonacci 2, sequence 2, and the value is 1 here, because it's 0, 1, and then 1. So here is the value 1. Let's see now if the go test -v. As you can see now you have a failure, test Fibonacci 2 here, line 30, test Fibonacci 2 was expecting 1, but got 1, 2, 3. So now let's go into the Fibonacci.go, and let's attempt to fix the test and attempt to fix the implementation itself. So we know that for the first two values our function works. Now we just need to make sure that it works for any other value. So we know that Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. And that's what the whole function is about. So let's now try to see with the go test -v. Everything works fine. So we have successfully fixed the test, and we can also, for example, just run through another test case just to be sure. Let's see that with the 10 one, 10 is 55, I already know that. So go test -v, it's working successfully. So it's 55, and we can also have other tests, but this is 6, this is 8, 13, 21, 34, and 55, 7, 8, 9, and 10. So those are our test cases. So now we have our test. All the test cases pass, but we have an issue here. We have a lot of duplicated code. How do we make sure that we don't have all this duplicated code? Well, the good thing about Go and the testing with Go is that it's not actually a framework or some very complicated library where you have to remember where you have to remember a lot of APIs and a lot of usages and functions. You have very, very, very simple and lightweight function calls and a number of APIs, so just error-f and fail. So in this case you can build your own way of writing tests, right? And one of the patterns that we usually use is the table-driven test. It has nothing to do with a library or with a framework-specific thing. It's just that you basically bundle all the test cases together, you loop through them, and you run the test in that way. So you don't have to duplicate all the code like this. How are we gonna do that? So we know that we have a bunch of input values and an output values. So we're gonna define the test cases as a slice of structs, and the slice of structs has a sequence number, and it has expected value here, which is what we're seeing here, so sequence number and expected value. But the thing is that now we can define a set of them all in the same function instead of declaring and copy pasting the code all over the place. So we're just gonna go through that. We're just gonna go through the definition here. So we said that we haven't actually tested the zero case, as we are testing the function down here, so we can do the same. We have this, for sequence number 0 we expect 0 as an output in the Fibonacci sequence, and then we can do the same for 1. So for 1 we expect 1, for 2 we expect still 1, for 3 we expect it to be 2, and then we can say, for example, for 5 we expect it to be 5, and then we can say for 10 we expect to be 54. So this is our the input, the sequence number, and the expected output, and then we need to make sure that for all those scenarios the thing is what we expect. So what we do, we just write a loop. We range through the test cases, and then we just do the thing that we've done before. So we just make sure that the output is what we expect. So the output here is Fibonacci of TC, which is test case. It's each and every of those dot sequence number, and then we need to compare that to what? To tc.expected. So tc.expected, and consequentially we have to also update the values here. tc.sequence number, tc.expected, and output is what we expect it to be already. And this means that we can delete all of this here down here, so we don't have to duplicate the code. We just have the test cases in there, and we can just go test-v 55, obviously, just not 54. Go test-v. And as you see, you just have one test case, one function, it runs all the test cases together. There is also something to do with the testing.T.run. So it runs subtests in separate coroutines. So it allows you to write, if you have very CPU intensive operations, you can use that to speed up your tests. And that's another thing that you can do once you have table-driven tests in there. So the t.run, it allows you to run in a different coroutine. Here is a test case name that we're gonna see now in a second. For now, just gonna have, say, test case number based on the number here, which we define while looping through the slice. And then the function, which is if it's a coroutine, it takes the same testing.T, and then all of this is going to basically be down here inside this function. So when you call t.run, what happens is that you will get those test cases, you will get those test cases running a different coroutine, as long as you then call t.parallel. This will run in parallel mode, and tc, obviously now what we need to do is tc test case, have we declared test case? No, test case is equal to tc, and here we're gonna use test case instead. Test case. This is because of the nature of the coroutines. because what happens is that if you don't reassign this TC value, you're always going to have the last TC value, because the coroutines don't get spawned necessarily when you are in this range. So the values may be different from what you want, so it's always good practice to reassign the value before you send it to the coroutine, because this TC value changes while you go through the loop, but the t.run is not guaranteed to be at the same time in which you are into the loop, so there is some synchronization issues there, and you also need to make sure that this is always being reassigned when you use the parallel notation when you go to the coroutine. Test case here, test case here. So just to recap, testing.T .run, we said runs f as a subtest of t called name, so you have to pass a name. Obviously now we just made up a name, we just said the test case number, whatever the number is, but if you have different test cases you can specify the name there. It runs f in a separate coroutine and blocks until f returns or call t.parallel to become parallel test. So it is effectively, if you don't call parallel, it's not a parallel coroutine, it's not for CPU intensive tasks, so it blocks, and you wouldn't need to reassign the test case. But if you want to make it parallel, you can just call t.parallel, and that will signal that it can be run in parallel, and that will speed up the test a lot. So now we just recap the Fibonacci test. We have our test cases as we have done before. Before we were running them sequentially one after one and blocking them one after one. You could also have a subtest, which is like a logical separation, and the subtest can work in two ways. The first way is by working sequentially as before without having the parallelism, and that will still block, but it allows you to have a logical separation of the test. And the second way, as we have done here, which allows you to basically speed up the test because you have some degree of concurrency into your tests. And once you have your function, you define the function name here. You have to define the test case name while it will still run, and then you pass the t.testing.t, which is exactly the same signature as up here, because the t testing package is what is being used throughout the testing of that, and allows you to trigger the failure of the function. And the rest is exactly the same, so you don't have to do anything else on that side. So now hopefully we should have some results. Obviously you would have to import all the packages using here. As you see here, everything is passing successfully. As you see, there's also some scenarios where it says it's pausing before running, and it gives you a little bit, a lot of details on the parallelisms of that. But as you see, everything is passing successfully, and that's the table-driven test with the parallel tests. So this is basically it for the Fibonacci function. So we have just went through how you can test your files. So remember always to use the underscore test for your files. So we know that all the logic for testing for a specific file is inside the underscore test suffix for that specific file. And apart from that, then the test, you can run the test using go-test. So that's the way you can run the test, and it will scan the directory for all the underscore test file. If you want to verbose mode, you can specify -v. That's another thing you can do. You also have the opportunity to specify test that runs in parallel, as we have seen. You also have the as we've seen here, you also have the opportunity to specify test cases using table-driven tests. So this is called table-driven test. You can specify different test cases by using the same function. And this is just a very simple example on a self-contained function. It doesn't have outside dependencies. And if you already got most of the logic around this use case, you got 80% or more of what you need to know to write unit tests in Go. So this is effectively all the language specific or the library specific knowledge you need to know in order to write unit tests in Go. We will see that all the other scenarios later on, when we have the external dependencies, are gonna be dealt with just by using dependency injection or other techniques, but the most of it is all around using the testing package, as we've seen today, and it's very minimal and it's very simple. So I hope you liked the tutorial, and if you have any questions, just leave them in the comments below. I'll try to answer them, and thumbs up if you like the video. Thanks.